our piece. So thanks for joining us, Anna. So please, you have 50 minutes and then we have 10 minutes questions. Thank you very much.
Thank you very much. So it's a great pleasure to have the chance to present our works to the conference, and please accept my apologies for not being able to be there with you in presence. So, okay, so anyhow, I'm going to present you today some works that we did on persistent currents in one-dimensional Bose and Fermi gases on a ring. So, let's see, just a second. Okay, the plan of the talk is the following. First of all, I will introduce the concept of persistent currents, and in particular focus on the properties of low-dimensional quantum gases, as this is the focus of the workshop. And then in particular, I will present two main topics. So one first part on attractive bosons, and I will demonstrate what we call angular momentum fractionalization. And then I will move on attractive fermions, and I will show you how it is possible to probe the BCS-PEC crossover with persistent currents, and also how to read out one-body and two-body coherence properties by this type of systems. All our works that I presented today are in these references here in collaboration with the group of Luigi Amico, as well as with the group of Hélène Perrin and Maxime Olchany. So let us start. First of all, welcome in Lineland. So as you know, even classical particles have constrained motion if you are in 1D, and it's the regime where interactions and correlations are the strongest. So this is a regime very challenging to study also in the quantum regime. The other thing that I would like to mention, because it will appear in the talk later on, is that in one dimension there are some types of excitation that are very peculiar, and these are the solitons. And here I put a palette of various types of solitons that were studied in classical fields, discovered in almost 200 years ago, and that are very well known in rivers and narrow channels. And even in Sicily, I found one of these solitons in a nice drawing. So anyhow, let us now focus in particular on this one-dimensional system. Let me recall first what I mean by one-dimensional. It means that all energy scales involved in the problem must be smaller than a typical transverse energy that separates let's say, the ground state manifold to the first transverse excited state. So in particular, this holds for equilibrium properties, but also for all that concerns the dynamics. So from now on, I will assume that this condition is always satisfied. And this is, of course, achieved if you have a very strong transverse confinement. For example, one-dimensional systems in a linear geometry are realized using either 2D optical lattices or chip traps. For what concerns the model for these systems, in effect of the interaction, you have to take into account the effect of the transverse walls to define an effective one-dimensional interaction strength. This was first derived by Maxime Olchany in 1998. And the effect of this study is to be able to describe the one-dimensional interaction strength as a contact delta interaction with an effective one-dimensional coupling constant that I will call G. The corresponding Hamiltonian, very generally, is the one written in the board. So it has a kinetic term. It may have a term of potential. It can be, for example, a barrier potential or a longitudinal confinement. And of course, we have the interactions, the delta contact interactions. In general, in one dimension, we define a dimensionless interaction strength which is given by the ratio of a typical interaction energy to a typical kinetic energy constructed with K vector associated to the density again. And this shows that it is possible to go to strong interactions, for example, by decreasing the density. Now, there are in fact two cases, as many of you know. You can have a repulsive interaction described by the case G larger than 0, or attractive interaction described by the case G smaller than 0. And in this talk, I will mainly focus on the case of attractive interactions. So, in general, the system the Hamiltonian that I just presented, in the absence of the external potential, is integrable by the method called the Bethe-ansatz. So the Bethe-ansatz for bosons was proposed by Lieb and Liniger back in the 60s of the last century, and it amounts of writing the many-body wave function in terms of the sum of various permutation of some amplitudes in front of plane waves. And so this essentially, since we are in one dimension, we can order the coordinates of the particles in a line and define several coordinate sectors, for example, x1 smaller than x2, smaller than x3, etc., but also all the possible permutation of these coordinates. And all this creates a huge space, or multidimensional, and it is possible to write the many-body wave function in all across this space, provided that we can match the different coordinate sectors by imposing that each time two particles meet, a cusp condition is satisfied, and this cusp condition replaces the effect of the interactions. So in fact, it is possible then to write piecewise as plane waves, but these K vectors are not the free particle K vectors, but are K vectors defined by the set of coupled transcendental equations. And so for arbitrary interaction, this must all be solved together. I have also added here a term which I will discuss just slightly later. It's the gauge flux. So I will come back to this term later on, but please keep in mind for the moment the general structure of this equation. And so there is the term related to interaction, thanks to this constant C of interaction, which is proportional to the G. And then we have a part related to some integers, ij or half integer, depending if we have odd or even number of bosons. And L is the size of the system, the one-dimensional system. Notice that if we have attractive interactions, then this Bethe equation have a complex solution that are called n strings. And this little n can be as large as the total particle numbers. Another extension is in the case of when you have fermions. For example, for two-component fermions, the Bethe-ansatz solution was found by Godin and Young, and is based on the so-called nested Bethe-ansatz, that is a Bethe-ansatz on top of the Bethe-ansatz. So I will not put all those equations in these slides, but please take into account, keep in mind that in general, it is always possible to write an ansatz for the many-body wave function, also for the multi-component system. So now, in particular, we are interested in the dynamics, and we are interested in what happens if I bend a 1D system onto a ring. That is, I consider a system with periodic boundary condition. This geometry is not only very practical from the theoretical point of view, but it also corresponds to the very useful geometry when when we want to study, for example, the effect of atoms under rotation. In fact, this ring geometry has two main so-called atomtronics applications. One is to have quantum simulation platforms. For example, in this case, we have no effect of the boundaries. The theorists know very well that this is the best boundary condition because we don't have to worry about the walls. but also it introduces new observables like the current, as we will see. And secondly, we hope to create new quantum devices with this system, in particular to apply for quantum sensing. So to describe these systems, we take as an input ideas from mesoscopic physics, because the system is of finite size, and from condensed matter physics. And we want to apply that to describe ultracold atoms. So this is the topic of my talk, and I will in particular focus on both bosons and rings and fermions on a ring under rotation. So it is experimentally, there is so far a great tradition of creating various types of ring traps. There are many ways to create ring traps for atoms, from the simplest toroidal shape potential to more advanced and more complicated intersection, for example, of tubes with sheets, and to use, for example, dressed potential states. In all cases, it is possible to create very smooth and broad rings. There have been a lot of activity in this field, which is summarized in in one roadmap and in a review of modern physics papers that we have co-written with Luigi Amico and co-workers. In particular, and now we come to the famous omega that was in the previous slide. If we have bosons or fermions on a ring under rotation, this by going to the co-moving frame, we can reabsorb the effect of this rotation into a so-called artificial gauge field. And in fact, this effect of rotation shifts the kinetic part, the momentum P, by some constant, which is proportional to the rotation angular, to the rotation frequency, to the angular frequency of rotation. So the general Hamiltonian has the following shape. We have a kinetic part. We have possibly an external potential, for example, given by a barrier. We have the interaction, and then we have a constant that we will discard from later on, because it's it's just a sort of a zero of the energy. So in this case, when we have rotating particles on a ring, it is important to introduce the concept of persistent current. And this is, in particular, allows to answer what is the question, what is the ground state energy in the presence of this gauge field? And in fact, that was studied in the past in the condensed matter community. And in particular, there is a lot long studies by Tony Leggett, which stated the theorem saying that the energy landscape for particles, quantum particles with repassive interaction, is always the same independently of the interaction strength. In particular, you see that it's a sort of parabola, so look at the bottom part, and each parabola corresponds to a different value of angular momentum, or a different circulating state on the ring. If I add, for example, a barrier, then I have a coherent mixing of these angular momentum states. Angular momentum is not anymore conserved, and we have a small mixing of the states and the opening of gaps. So now the persistent current is defined as the derivative of this ground state energy landscape with respect to the applied gauge field, omega. In the co-moving frame, then it's a sort of sawtooth picture, which going back to the lab frame corresponds to a stepwise increasing function, which counts how much angular momentum we have in the system. If we apply a barrier onto it, there is a smoothing of these angular momentum steps, which is more and more marked the strongest the barrier strength. So in particular, for repassive bosons, we have studied the effect of this amplitude of the persistent currents, that is going back to the previous slide, is this difference between the maximum and the minimum of this persistent current in the moving frame. And by a combination of several techniques has given a very, very rich panorama, in particular showing that this persistent current amplitude is non-monotonous. And there is a weakly interacting regime where interaction screen the persistent current amplitude and then screen the barrier, and then the persistent current amplitude increases. And then there is a regime, a quantum regime, where this amplitude decreases again because the quantum fluctuation, let's say, can renormalize the barrier strength. And we have combined these studies with different methods. So the Lattinger liquid theory, for example, the limit of infinite interaction strength, as well as the numerical DMRG calculation. So this shows an example of a quantum state manipulation. That is, we can create some state where, for example, the barrier strength can depend on the interaction regime. It is also useful to know if you want to study transport across a barrier or even more exotic situations. In particular, this study shows that it's possible to conceive and control a so-called flux qubit that is a superposition of current states. This is what is interesting by looking at the state where zero angular momentum and one angular momentum become degenerate. And so this is just an example of an application of the study of these persistent current states. Now, let me concentrate on, let me focus on the case of attractive bosons. And in this case, the idea is to explore what is the fate of the persistent currents in the system. For this study, we have used a lattice model. The reason being that for the bosonic case at finite interaction, on the lattice, the system is non-integrable, but we can use numerical methods to address it. And also, of course, lattices itself are a possible realization of this type of ring structures that has been proposed in the literature. So to introduce the rotation in a lattice model, we used a well-known Peierls substitution. That is that we have a tunnel amplitude that becomes complex. And it is related to this hopping term, the first one here. And then, of course, we introduce interaction, on-site interaction proportional to the interaction strength U on the lattice, which is a negative constant to describe attractions. The calculation by diagonalization of allows us to obtain the ground state energy as a function of the artificial gauge field omega. And this is the first very surprising result that we obtained that shows that if we have more and more particles at a given interaction strength, we see that periodicity of these parabolas, so this is the ground state energy branches, the periodicity of these parabolas increases. So in this case, we see a breakdown of the Leggett theorem. In this case, it does not apply. And in particular, correspondingly, the persistent current have a smaller periodicity as well, which could be useful because it has an enhanced sensitivity to the value of the artificial gauge field. So what does this come from? This comes from the quantum state, and this quantum state is a many-body bound state, or which can be viewed as the quantum equivalent of a soliton state. Essentially, this is like a soliton-like structure occurring in each site of this lattice potential. And it is a circulating state. So let me now to demonstrate this this 1/n periodicity of the ground state energy, we go back to the continuum model because in this case we can use the Bethe-Ansatz solution. This Bethe-Ansatz solution does not describe the lattice case completely, in particular because in the lattice it's not true, but here the center of mass and relative coordinate decouple, but still it is an interesting way to demonstrate this reduced periodicity that we observe also on the lattice. So first of all, if I want to calculate the ground state energy of this system, I have I just plug into the Hamiltonian the wave function, and I calculate the expectation value of the Hamiltonian, and I obtain that it is made of two parts: a part due to interaction, which depends only on the relative coordinates and is not affected by the rotation, and the part which depends on the center of mass of the system and which is affected by the rotation shifted by n times a typical momentum associated to the rotation. So in particular for repulsive interaction, we have that the center of mass momentum of this system is always an integer times the total number of particles times h bar over the radius of the ring. So and this comes from the Bethe-Ansatz solution. When we calculate the total momentum of the system, all the terms are associated to interactions cancel out, and we have just the integers. If you remember in the Bethe-Ansatz that we had some integers, the integers defining the state of the system. And so this immediately demonstrates the Leggett theorem, because we have that the ground state energy is a periodic function of the reduced flux omega divided by omega 0, where omega 0 is the typical frequency associated to the quantum of flux. Now, if we do the same calculation for attractive particles, in this case, as I told you, the ground state is a many-body bound state. Well, in that case, all the particles have imaginary rapidities and form a n string with n equal to the particle numbers. That means that in the real part of the wave vectors, they are all the same, and I can construct a center of mass state which carries the momentum, which is just h bar over r, like a single particle. Just this particle has a mass n times bigger than the mass of a single particle. This is the mass of the many-body bound state. So you see that if I plug this center of mass value into the ground state energy, I obtain immediately the 1/n behavior in the ground state energy. So what does that mean? In fact, if we now let's go back at the current in the lab frame, we see that angular momentum in this system of attractive bosons increases in small steps that are fractions of h bar. So the total many-body bound state can carry one quantum of angular momentum, but that means that each boson has a fraction of angular momentum. So we called this angular momentum fractionalization, and it is an effect due to interactions. Let me notice that this effect is a truly quantum effect, cannot be found at mean field level. For example, we have tried and we have solved the Gross-Pitayevsky equation for the same system, for attractive interaction, adding the rotation, etc., etc. And this is the energy as a function of the artificial gauge field that we see. And you see, it is smooth. It is missing all the small steps that we were finding in the quantum problem. A posteriori, this is also clear because the Gross-Pitayevsky energy does not resolve the single particle. It is a large number of particles, a large n expansion. So it is a sort of an interpolation between infinitely tiny steps. Another aspect that I would like to mention about our work is that since we are on a lattice, We do not always have a perfect 1/n fractional, 1/n periodicity. What we may have is also intermediate landscape, as shown here in the inset. I hope that you see. Or in other words, as shown here in the main picture, the steps in the angular momentum can be of different size and different width. And this happens when the interactions are not sufficiently strong to allow to form a very well-defined many-body bound state. So it is an extremely rich system. And let me now mention one application to quantum sensing. So in particular, let me say that quantum sensing is already something that is employed to measure gravity with ultracold atoms. And atom gravimeters are not only existing, but they are also sold and can be bought. It can be used, for example, the gravimeter, for example, can be used to identify underground water masses or oil, or to get different type of masses underground. So in all cases, the idea of this type of gravimeter in a nutshell is to create an atom interferometer and then look at the interference fringes and then read out from these fringes the quantity we are interested in. For example, in a gravimeter, we want to measure the acceleration A. And of course, it would be great if we could increase the precision of this measurement by increasing the slope of this interference fringes curve. And that is, that would be possible if we could use a non-classical state to make this interferometric scheme. So this is the so-called quantum advantage, that is to get a precision which is not achievable with classical devices. For example, this was already known with photons, but it would be great to have it also for atoms. And in particular, it would be interesting to use the same idea for rotation sensing. In this case, we would like to create a state which is a non-classical state of currents. So one idea to create such a state is to follow the following protocol. We start with no applied flux, and then we do a sudden quench, a sudden change of the flux value omega. And we do such that we jump just in the middle at 0.5 omega 0, just in the middle of the two big parabolas. Now, if we follow the time evolution of the state of the system following this quench, we find out that after a quarter period, we have a perfect fidelity to a state that is a so-called null state, that is a superposition state between having all the particles that have angular momentum 0 and all the particles that have angular momentum n. So we have tested that if we now look at the quantity that is useful in atom interferometry, that is called the quantum Fisher information, this quantity scales as the particle number square, and the system is very small, so we could try 2, 3, 4, 5 particles. And why is this quantity important? Because it's the phase sensitivity is related to the inverse of the square root of this quantity of the quantum Fisher information. So that means that thanks to this protocol, thanks to the attracting bosons, it could be possible to reach Heisenberg limited precision for atom interferometry with current states. Okay, so that is the first part of my talk. And now let me turn on to the case of attracting fermionic matter. So first of all, when you have Fermi gases, first you may think whether it still makes sense to define the concept of persistent currents, because you are mostly used to supercurrents flowing into superfluids. So in fact, the persistent current, let me stress, is a concept completely general, and can also be defined and can also occur in non-superfluid systems. It is enough to have a quantum degenerate gas that is a quantum degenerate all through the ring. So in particular, it can occur also in Fermi gases. But of course, it will be particularly interesting to study the case when Fermi gases become paired and then you create a superfluid or supercurrent of paired Fermi gases. So, but one step at once, let's first start from the properties of persistent currents in non-interacting fermions. So, in Fermi gases, there is one effect that is not found in Bose gases that is called the parity effect. If I calculate the persistent current for an odd number of fermions, I get this type of picture. The energy as a function of omega has a minimum in omega equals 0. However, if I take an even number of fermions, I see that there is a maximum, not a minimum, at 0 flux. And in fact, this is the difference between diamagnetic or paramagnetic response to an effective magnetic field. And it is readily explained if you think of the Pauli principle, the way you feel energy fermions into a Fermi sphere. This one is the following. You have, for odd particle numbers, you have -1, 0, and 1 for 3 fermions. But if you have only 2 fermions, you have actually 2 choices. Either you put them in 0 and 1, or you put them in -1 and 0. So you have 2 branches, in fact, by turning on the flux, which are this one on the right and this one on the left. Okay, so on the other hand, there is no parity effect in Bose gases, not even at strong interactions, which is a priori a surprise, since we know that if we have Bose gases, the exact solution at strong repulsions is mapped onto the one of a Fermi gas. But still, I have no time to demonstrate it here, but there is no parity effect in Bose gases. Okay, so then there is a very important theoretical question that was raised in this work by some of my Grenoble collaborators, so a researcher group in Grenoble, so my colleagues. If you take in particular even particle numbers, even particles of an up and down, then they demonstrated that the energy is always larger or equal to the one at 1/2 at omega over omega 0 1/2. They used the notation pi here, but there is nothing is said at 0 flux, and they were suspecting 2 scenarios, either a maximum or a minimum at 0 flux. So what happens really? It depends on what type of state we have. So let me show that we have a specific answer to this question in the case of fermions with attractive interactions. Let me consider here the model for fermions. Let me introduce this model. It's the Fermi-Hubbard model, again on a lattice, subjected to an artificial gauge field. And again, the interactions U are attractive. In this case, since we have fermions, we consider 2-component fermions in order to have interactions in S-wave. Otherwise, there are no S-wave interaction for spin polarized fermions. At the difference from the lattice bosonic case, here we have an exact solution by Bethe-Ansatz due to Lib and Wu. And about the physics of this system, if we have large attractive interactions, there is a limit of infinitely large attractions, which corresponds to a Tonks-Girardot gas of tightly bound pairs. And this was demonstrated in the thermodynamic limit by Idia and Vadati, which have shown that the Bethe-Ansatz equation for the ground state of the fermionic model coincide with the one of a bosonic model, provided that the mass of the bosons have twice the mass of the fermion, and the density of the bosons is half the density of the fermions. So then, by tuning the interaction strength, we can explore the BCS-BEC crossover in one dimension. That is, we can go from a regime of weakly bound pairs in the BCS regime to a regime of very tightly bound pairs that form a Bose-Einstein condensate, or the best it can form in one dimension. And all this goes across the equivalent of the unitary regime, where let's say it's the most strongly correlated regime among the two. So in order to model this system, in fact, we follow a prescription suggested by Fuchs, Recati, and Zwerger, which noticed that, in fact, a simple Fermi-Hubbard model, or the equivalent on the homogeneous case, does not allow to go beyond the infinite attractions. The model is too simple, but then we complement it with another bosonic model on the BEC side. Notice that we could do better. For example, take a boson fermion model, as it was, for example, suggested by Ren and Alainer, but was not the main goal of our project. So we decided to stick to the simplest possible model. So then in our case, then we calculated the ground state energy and the persistent currents as a function of the applied flux. So to the fact that the particles are set, the fermions are set in rotation along the ring. So we start as a test from the non-interacting case. These results are for 3 spin up and 3 spin down fermions. And we see that we recover the typical landscape that we were obtaining by the, say, back on the envelope calculation for non-interacting fermions. And then with our non-interactions, attractive interaction, the first thing that happens is that an excited state up there starts to decrease in energy. And here you see it forming. We have a sort of superlattice, so double, one, let's say, periodicity 1, but an extra structure that starts to be formed. Finally, if we have a very strong attractions, then we form a ground state energy that has a double periodicity as with respect to the non-interacting fermions. And notice that this periodicity is exactly the same of the one of bosons for the same system. And so we have a second example of breakdown of the Leggett's theorem. In this case, this change of periodicity is due to the formation of the pairs in the system. So we see that we can use persistent current to probe the pairing properties. In particular, we can tell whether we are in an intermediate regime of attraction or in a very strong regime of attractions. And now let's see what happens to the fate of the parity effect that I told you was a typical fermionic property. So for here I compare the case of 3 + 3 fermions with the case of 2 + 2. And in the case of 2 + 2 fermions in absence of attractions, we have this V-shaped energy landscape. And if we increase the attractions, we see that both for even and odd particle numbers, we have a doubling of periodicity, but in particular for this even case, we see that we have completely lost the parity effect. There are as many branches as it was for bosons. And this is another indication that since the pairs behave as bosons, there is no more parity effect. It's very cute, I find. So another issue that it was possible to study for us were the finite size effects. In particular, the fact that since we are on a ring, we cannot host pairs that occur for 2 weak attractions. We have, in fact, a critical interaction strength above which the pairs start to be formed. And we see that from the Bethe-Ansatz solution. But we also see that if we take a larger and larger system, the number of, so the critical interaction to get onto this paired state decreases. And so we agree with the prediction that is in the thermodynamic limit, we can form pairs at infinitely weak attractions. Finally, in the last part of my talk, I would like to discuss the readout of these current states and in general other things that can be understood when we imagine some interference protocol. So in particular, the interference protocol that we are interested in is the one where, in addition to having a ring lattice, we add an extra site at the center of the lattice. And then we turn off the traps and we let expand the ring lattice and the central disk. And we look at the fringes. And we can expect that since the currents are associated to phase gradients, then they will be visible in interferometry. And then let me show you what happens. First of all, thanks to this expansion, each lattice rings interferes with the central dot. For example, these are the fringes of the site number 3 with the central dot for a state which carries 1 quantum of angular momentum. Then let us look at the interference fringes for the site number 2. They look more or less the same, but let's go back. The position of the blue fringe with respect to the dot is slightly shifted, you see? And it's more even visible if you look at the site number 1. Now the blue line is really on top of the site. Now, if you sum all these effects, you see that the corresponding interference fringes takes the form of a spiral. So you see that it is quite easy, at least in principle, to detect the current states by doing this type of interferences. And in fact, for bosons, it was already employed in 2 experiments, one in Paris and one at Nice. And both were able to tell the sign and the amount of circulation of the current. So in the case of interacting systems, the spirals emerge in density-density correlations, as I will just show you in a moment. In particular, if we now calculate the spiral interferograms for our system of 2 + 2 fermions, we see that if we fix one value of artificial gauge field such that we occupy the parabola here that corresponds to 1 quantum of angular momentum, we see that we have a sort of a spiral associated to a dislocation. Instead, if we have attractive interaction and we are occupying the central parabola corresponding to no circulation, the spiral interferogram are top-bottom symmetric and are not spiral-like. And this is quite general, and it shows that we can probe whether we have a 0 or 1 quantum of angular momentum in the system by looking at the type of spirals. We can do the same just as a check at larger value of angular momentum of applied artificial gauge field. In this case, for all value of attractions, we are always in a parabola at fixed angular momentum 1. And we see that in all cases, we have a sort of spiral-like structure. Now, if I still have, yes, I think so. I have about 7 minutes according to my watch. We can briefly discuss how this can be used also to probe coherence and correlations in Fermi gases. So, in general, the coherence of a Fermi gas is a very abstract concept. While for a Bose-Einstein condensate, it's easy to visualize the coherence because all the particles share the same macroscopic quantum state. For fermions, we know that we have many orbitals occupied. Nevertheless, some coherence can emerge, for example, the coherence among pairs. So we have to find out the way to probe this coherence. And the most rigorous but also operative way to prove this phase coherence is to look at off-diagonal long-range order of pairs. This was proposed by Young back in the 60s. So for bosons, it is enough to look at the one-body density matrix, so the 2-point correlation, and for fermions to the 4-point correlation or two-body density matrix, spin resolved, because to make a pair, we need a spin up and spin down. So this is the pair-pair correlation function. So to prove this pair-pair correlation, I will show you that it emerges from the expansion of this ring at large distances, while at intermediate expansion times, we access just to the one-body coherence. So going rapidly to across the one-body coherence, the interference with of these released atoms with the central ring by employing all the expansion into orbitals, we immediately obtain that this density-density correlation is related to the first-order correlation of the fermionic gas. And in particular, before you had seen a spiral with one dislocation, let me show you that it is very general. And if we have more particles, we have still a spiral with more dislocation. And so if we compare to non-interactive bosons, this type of coherence is clearly reduced, and is due to the fact, in fact, that Fermi statistics inherently reduces the first-order coherence. So now let us search for the pair-pair correlation. And this is achieved at long times, because in this case, when we study the expansion, then the same as when we look at the time of flight, also for the density-density correlation, the expansion gives rise to momentum-momentum correlation between, in particular, between spin up and spin down momenta. So we calculated this type of correlation function. It is a four-dimensional correlation function, so I represent it by fixing two coordinates, y and y prime equal to 0, in the plane x and x prime, which correspond, remember, to k and k prime correlations. So first of all, let's look at what happens for repulsive fermions. And the correlation are mainly across the diagonal, k equal to k prime. Now let's turn on attractive interaction. And we see that indeed correlation emerges in this case along the anti-diagonal, k minus k prime. And this is a clear indication of pairing. So at weak interaction, we have some correlation essentially around the Fermi sphere, the Fermi points in one dimension. And at strong attractions, we have a correlation all across the diagonal, indicating that we have point-like pairs in real space. Now we can learn a lot from this anti-correlation diagonal, because if we apply, for example, an artificial gauge field, we see that the position of this diagonal is shifted in steps, and magically, these steps are fractionalized, again allowing to see that we have pairs in the system. This is a way, a quantitative way to probe this doubling of periodicity of energy levels. The second thing that we learn from this diagonal is the following. If we rescale now and we look at the visibility along this diagonal, that is, we take the maximum of the intensity minus the minimum of the intensity divided by the sum, then we see that this visibility for attractive interaction, all the data collapse on a single curve. This is not the case for repulsive interaction. This is the right part of this curve. So if you think a bit, this is a proof of a quasi-off-diagonal long-range order in this system. This because if we look at the two-body density matrix along the diagonal, if we had full off-diagonal long-range order, which is, let's say, approximate because we are in one dimension, then we would have that the that we would have that this two-body density matrix would be fixed by the pair wave function. And the prefactor would be its largest eigenvalue, depending on the particle numbers. Now, if I apply the visibility to this expression, we see that there is a cancelling on the dependence of the number of particles between the maxima and the minima. And so the collapse is a clear indication of the formation of quasi-off-diagonal long-range order in the system. So we have an operative way to test this quasi-off-diagonal long-range order. Okay, so this brings me to my conclusions. I have shown you that the study of the persistent currents in ultra-cold atoms, and in particular in one-dimensional quantum gases, is very rich. In the case of attractive bosons, it carries the signature of the formation of many body-bound states. And in the case of attracting fermions, it allows to probe the BCS-BC crossover and to probe both single particle and two-body coherence in the expansion. So I would like to conclude by thanking my collaborators. This has been a set of works that were inspired by Frank Hecking, who was my mentor and who unfortunately passed away. But we continued his work together with Luigi Amico, Juan Polo Gomez, Giovanni Pecci, Piero Landesi, Maxime Olchany, and Vanya Dunko, and Hélène Perrin. So it has been a great pleasure for me to present this work to you, and I am now ready to answer and to listen to your questions. Hello?
Adana, so questions?
Hi.
Well, I have a question. When you made this system of composite fermions behave like bosons and showing the same patterns, in principle, we know that, in fact, fermions are fermions and bosons are bosons, at least when they can show some pattern, but in the end, they are fermions. So in principle, you can detect some observables that they show that they indeed are fermions, some correlations beyond. Can you comment on this, please?
Oh, yes. Okay. Yeah, indeed, we were. I would say that the first signature that they are fermions is in this fact. If you look at this here at these images, you see that we have these dislocations. And it's interesting that this dislocation is a number of fermions -1. So for bosons, we have no dislocation. They all occupy the same quantum state. And so I would say that this is one of main signatures that we see in these correlations.
Yeah, but there was a picture you showed that the fermions behave exactly like bosons.
You mean the currents? Well, in the persistent currents is a case where
this case.
This case is because the persistent currents they look at the structure. So it is just the response to the center of mass of the system to this applied gauge field. So it does not look at the internal structure of the pairs. For that, you do not have to look at the persistent currents. Yes, somehow it's the observable that is not designed to probe the internal structure.
Okay. Any more questions? No? So let's thank the speaker. Thanks a lot, Anna.
Thank you. Thank you again for the invitation.
Thank you very much. So next speaker. Sure.
Proukakis from Newcastle, who is going to tell us about criticality, quench dynamics, and phase ordering in ultracold gases. Please, Nick, the stage is yours.
Okay, thank you. Can everyone hear me okay? Do tell me if I talk too loud, because I get excited and I never ever use a microphone because I talk loud. So, you know, if I take your ears, please let me know.
I think it's okay.
So it's a pleasure to be here. Plus I wear a mask. I've been wearing a mask for so long time now that I don't really know the volume that I actually churn out. It's a pleasure to be here. And well, the topics of what I'll be covering is very related to a lot of other things that have been discussed here. Let me just check the laser pointer. Which one? Ah, there we go. Okay, so I have a complex title, Criticality, Quench Dynamics, and Phase Ordering. And the idea is I'll be discussing about non-equilibrium physics. And I have a lot of things to say, which are all related to various things that have been raised here about non-equilibrium physics. And in principle, I'll probably only be talking about cold atoms, but I have various other things that, depending on how we go along, I don't want to rush this, then I could mention for other systems. So I'm going to start by giving some kind of introduction to criticality and equilibrium criticality, so I can then discuss non-equilibrium features. And then I will be focusing on cold atom quenched experiments and talking about the issue of Kibble-Zurek, so a system falling out of equilibrium, and then seeing how the system regains equilibrium afterwards. I'll be making various references to the role of dimensionality and homogeneity in some places. And everything okay? Yeah, okay. And tell you a bit more as outlook. So in principle, I want to answer one question. It's a very general question, okay? We start with something which has no coherence, and we want to form something that has coherence. How does that happen? And how does that happen in a dynamical way? This is really the question I want to address here. Oops. So, Vanderlei already mentioned this, this review chapter here. If you're interested in finding out more about the things I'm saying today, I've just completed another review, which is to appear at some point in this Encyclopedia of Condensed Matter Physics, and it will be on archive. I should have got my act together and put it on, but I haven't. So it should appear next week or the week after on archive. So what's the idea then? Well, let's start with equilibrium picture, okay? Here I have something which is non-equilibrium. This is inspired from the experiment I'll be analyzing in elongated condensate for Trento, and this is a corresponding 2D sort of system. And then eventually, at some point, we cross through and have something which is an equilibrium condensate of some sort. Okay, so there's a critical point, of course, that we cross, and if we're talking about a thermal transition, then it's a temperature, but there can be many different control parameters, of course. And it's not really a point, it's a region. So what happens in the vicinity of that region is absolutely important. But when we now cross the transition dynamically, what happens, of course, is there's a certain element of time delay as you're trying to cross. And so we need to generalize the concepts of equilibrium criticality to how we go dynamically. And at some point, so you arrive at something which is highly non-equilibrium at this point. You're crossing the phase transition, and then the whole thing needs to relax so that you get something that is your final equilibrium as prescribed by the energy, the particle number, geometry, homogeneity, and so on of your system. Okay? And of course, there's a whole field of sort of universality and statistical physics that deals with aspects of criticality near the critical point and universal features. Okay, so this is the question that we want to address. And of course, universality is a very big word. And it means many different things, and I'll only be touching on some aspects of universality. So the kind of thing that is relevant here, we are driving a system through a phase transition. So there's this phenomenon that I will be describing, although most of you will be familiar, about Kibble-Zurek mechanism of how you cross the system. Once you then relax, there is the whole process of phase ordering. How does that random, highly non-equilibrium state relax to something that has a lot of coherence in it? But there's many other aspects of universality. And I'll just briefly mention two, although I won't be touching them here. The first one was mentioned by Vanderlei. It's in the context of these non-thermal fixed points. Okay, I will not really be discussing anything about that, but of course, you have universal features of equilibration, slow relaxation around these non-thermal fixed points. And Marcena Simanska will be talking a little bit about emergence of KPZ or Kadar-Parisi-Zhang universality. That's another form of universality. Each of them is different, and I'm not going to be touching on all of them, obviously, here. But I just wanted to mention this context because people talk about universality, and usually you always think of something in particular, but there's many, many occurrences and many more. And central to all of these, I don't have a plot of that, is of course turbulence, Wandeley's favorite topic. So the idea, all of this is some kind of non-equilibrium system, well, not maybe KPZ, but some non-equilibrium system, and somehow it relaxes to something. So I'm going to be focusing on sort of Kibble-Zurek and phase ordering kinetics here. Okay, so let me tell you a few of the things of how we characterize system. This is probably well known to all of you, but just to get the language going. Of course, when we think about phase coherence, well, we think of high dimensional phase space density, okay, dimensionless. Okay, so D here is the dimension. Of course, we have to have a lot of particles for the characteristic properties of the system to have quantum degeneracy. The probes that we use to characterize this system are, of course, just densities and correlations. Okay, so if we have true Bose-Einstein condensation, then of course we talk about off-diagonal long-range order. So the idea that the one-body density matrix or first-order correlation function basically reaches some kind of plateau within your system size and doesn't decay all the way to zero. And that is, of course, a 3D kind of consideration. This is important when we think, as I will in a couple of places, talk about lower dimensionality. So I should note already here, of course, in 2D, there is no off-diagonal long-range order. One talks about quasi-long-range order. And then if you're thinking about the decay of the correlation function, rather than tending to a constant plateau at the edge of your system, it actually decays, but not with the exponential decay, but with the slower algebraic decay signaling sort of quasi-long-range order. Okay. One thing that maybe is a bit less known and is absolutely crucial to the analysis I'll be doing here is how we characterize what we're going to be seeing in the simulation. And it's all done in the context of this Penrose-Onsager condensate mode. So take your one-body density matrix and basically consider its eigenvalues, okay, eigenvalues and eigenmodes. Now, if you have a true condensate, then of course you expect, if your system is just a condensate, there will be one mode and all your particles will be in that one mode. But in a realistic system, you will have more than one mode. And so it's a matter of how strict you want to make your definition of condensation in a realistic, homogeneous, finite-sized and typically inhomogeneous system. So typically, one speaks of, well, if you have one eigenvalue, which is much larger than the rest, then this corresponds to the condensate. What much larger means can be a matter of choice, but certainly it has to be at least a few times. It doesn't have to be a few thousand times, but obviously you have to have a clear distinction of one mode from all the rest of the modes of the system. Okay, so typically it's sort of we say it's of order the total number, but it's a very loose definition. And I'll be showing you, when I'm talking about the condensate in the analysis later on, I'll be mostly showing you this Penrose-Onsager condensate mode, just the one mode that is the largest mode at the given evolution time. Now, of course, one can think about second-order correlation functions, and we were just hearing about them. Well, we've heard about them many times. I'll only be thinking about local second-order correlation functions here, not non-local, but of course, one can look at that. And we all know very well that due to the nature of density fluctuations, if you have a pure, if you have a pure condensate, then basically this is 1 because it's local. So we just probe this as a function of the location in the trap. If it's chaotic thermal, then this is 2. And so this spread will give us the amount of condensation, if you like, or coherence in the system. But this also relates quite generally to a concept in lower dimensional systems. Now, I spoke here about one mode, the Penrose-Sage condensate mode, but we really generally only have a condensate in 3D systems, okay? And generally, in most other cases, so in 2D systems, or in the case of turbulence or something, we can have many competing modes. So we might have modes that are largely occupied, but there won't be one of them. There might be 10 or maybe 50 of them or more. So that tells you how much you have one preferred mode as opposed to combination modes. And you can identify a thing called the quasi-condensate, which effectively is your density, but with suppressed density fluctuations, but it still has phase fluctuations. So it's consistent with the absence of off-diagonal long-range order. Okay, so now we come to the question then, how does the system choose, how does symmetry break as we go along? And let me start with a little bit of a sort of historical background on that. So let's go back to a pioneering paper by Tom Kibble in the context of the hot Big Bang theory. So in this paper here, obviously the idea of symmetry breaking is quite a general idea, but in this paper here, topology of cosmic domains and strings, what he was considering is the formation of what he called proto-domains as the universe is cooling. Okay, this is a hot Big Bang that is meant to be cooling. And so the question he asked is, well, he said there's an order parameter which varies from region to region in more or less a random way. And then he asked the question about regions being trapped like flux tubes in a superconductor. So the idea of trapping defects in the system in the same way that we do in cold quantum matter, for example. Okay, and this was taken up a lot and brought to the condensed matter realm by Wojciech Zurek, and he's been working, among the other things that he does, on these topics in many different systems since then, actually. And he discussed the analogy between cosmological strings and vortex lines in the superfluid and came up with the first suggestion of how to characterize these and so on. Okay. So of course, this idea of getting all these defects, this Kibble-Zurek mechanism has been studied in a lot of systems. Okay, cold atoms is not the first and probably not the last system where this will actually be studied. A lot of condensed matters have been seen, and they all have their own different specifics in the signatures and the kind of things that one can observe. Okay, and if you're interested in this Kibble-Zurek stuff, then Adolfo Del Campo has written 2 reviews, one also with Kibble, but this one is really great, so I recommend it. Okay, so we're going to be talking about crossing the phase transition, and so we should talk about what is the equilibrium properties around the phase transition. And I'm sure you all know, in the region, in the critical region, so very close to the transition point, then basically you have certain divergences taking place, okay? So if you look here in the case where there is basically 0 condensate fraction, so at the point where the condensate fraction starts growing, and you ask the question, well, what does the correlation length do as you're moving from above TT to below? Okay, and this is a graph I stole from a paper of Esslinger and Michael Kohl. So the idea is here, you're seeing how the correlation function is changing, and as the correlation length diverges as you approach the critical point. And in line with critical physics, the idea is that you can map this divergence in terms of a parameter that contains all the microphysics, and a parameter that tells you the deviation, the distance from that critical point with some characteristic exponent. And then a lot of the, basically the idea is to get generic features in the context of what is the value of the critical exponent for the system. This is equilibrium, so this is the static critical exponent. And this was measured in this experiment I mentioned, from which I took this schematic, and was found to be the expected one. So this is the one for the 3D XY model, for example. This is the one you expect liquid helium and atomic gases to be in. So what about time now? We're talking about a non-equilibrium time, a non-equilibrium system. And the idea is that as you approach this critical point, there is also a divergence of the relaxation time. Okay, so as the system is trying to approach this critical region, it takes longer and longer for the system to relax to that position. There is, again, a divergence here. The microphysics is all hidden in this tau zero, and all of the interesting stuff is in this exponent, which is now the static exponent times another exponent z, which is the dynamical critical exponent. And so the critical exponents will depend, basically, will define, if you like, the universality class of the system, their values. So in both of these cases, criticality is then, putting it in more general language, introduced in the context of a distance to criticality, how close or how far you are from that critical point. Okay, so let's consider then now driving the system. So we start from an equilibrium above TC and we want to drive to below TC, okay? So we start with something which is incoherent. There's all of random phases, no net mean field, and we want to get to the case where we have this famous Mexican hat potential, where we have a non-zero value of the order parameter with some phase that is fixed but has been randomly selected through the process. So our driving parameter now will become time dependent. Okay, it's linear in time in terms of this quench parameter tau q that tells you how quickly you're crossing the phase transition. And if I define the ratio epsilon over epsilon dot, this has units of time. So this is a characteristic time that will tell us about the dynamics of the system and the properties of the system. So the divergent relaxation time can now be written in terms of this distance to criticality and some of these critical exponents. Okay, so now what we're doing is we're driving the system. Imagine I start at above TC and I want to get to below TC. So I'm going to somehow change the parameters to make sure that the system goes in this direction. Okay, and so I'm doing that, and in the simplest way, I'm doing that linearly as indicated here. Okay, 0 denotes the point of, and time 0 denotes the location of the critical point, the equilibrium critical point. And so as I'm trying to approach that point, it takes longer and longer for the system to relax. So the system cannot really relax. And at some point, I'm actually driving the system faster than the time that the system can actually adjust. So there's no way the whole system can continue operating as one and maintain the equilibrium properties for the corresponding parameter, but it develops, it grows locally. So it develops symmetry breaking. Different parts of the system behave differently. And this is the so-called impulsive regime near the critical point. Okay, so as it enters from the incoherent side, we have this critical slowing down because of this divergence in the relaxation time. And the whole system cannot follow the external drive. And what happens is we have local coherent patches of, well, developing constant phase emerging, okay? Now, the size of these patches is given by this characteristic length scale, which we know is itself diverging as you approach the critical point, okay? So the point is that the value at which the system falls out of equilibrium and breaks the symmetry, that will tell us how fragmented, if you like, the system is at that point. So we have two time scales. One time scale shown here is the divergence of your relaxation time. And the other time scale shown here is the time scale associated with basically crossing the phase transition, okay? It's associated with this control parameter epsilon. And so different physics will emerge when you're quenching at the time where the system cannot instantly adjust as a whole. So at that point, that's when symmetry breaking occurs. We call that time t hat, or rather minus t hat, because it's on the left of the transition, is the characteristic time when the system breaks its symmetry, okay? So at that point where those two curves meet, that's where we have this critical dynamics taking place. So we know that the relaxation time diverges in terms of this distance to criticality measured at this point. Well, it should say here really t minus t hat, but it's symmetric in this cartoon picture, so it doesn't matter, okay? And then it is the same as the modulus of epsilon over epsilon dot. It's a negative curve, but it's the modulus of that is positive. Okay, so when we equate these, now what we have, if I just show you that again, we actually can get a condition that relates basically the system, the point at which this happens, the critical time, in terms of our quench time parameter, tau q, how quickly we are crossing the system. And as such, we can see in terms of this quench parameter, what is the value of this t hat in terms of these critical exponents z and nu that I mentioned. We can also identify at that point what is the relevant length scale of the system, okay, which is again given in terms of these critical exponents and the rate at which we are quenching. And of course, if you have a typical length scale in the system and a larger system, then you can get a typical number of domains that form there. And these domains will be separated by defects. So you can actually calculate the number of emerging defects and the scaling of this number of emerging defects. If you go very slowly, the whole system adjusts rather well. And so you get few defects that eventually equilibrate. But if you go very fast, then you will get many, many domains. And then there's a competition of these domains. And so the time scale of evolution can actually be slower here. It takes longer time for many fragmented defects to make one main defect rather than if you have a few. Okay, so this is basically this cartoon idea of Kibble-Zurek. Okay, so the idea is the average size of the domains is actually set by the equilibrium correlation length at the point where the system falls out of equilibrium, this freeze out time. Okay. The quench time scale is characterized by tau q. Remember, this is in the denominator of the epsilon of t parameter. And if tau q is very large, so very, very slow quenches, if tau q is very small or very large, then we have the limits of basically being either adiabatic or instantaneous. But in between, we have the relevant regime and a very large parameter regime, where basically the only relevant parameters near the critical region is this time scale t hat and the length scale psi hat. And so the Kibble-Zurek hypothesis says that basically within that regime, so in the critical region, you can, you can scale, basically time to t hat and distance and wave vector to psi hat or psi hat to the -1, or you can write that as some kind of scaling of the correlation functions, if you like. It's basically the same thing. These are the characteristic time and length scales, and this is how the correlation functions scale. And so there's a whole zoo of cold atom experiments seeing that in different geometries. So in a kind of 3D geometry, elongated 3D, the original Zurek suggestion of a ring trap, in a 3D box trap, 2D box trap, fermionic superfluids, and so on. They've all seen some of these features of Kibble-Zurek. Okay, let me just quickly mention the ring trap. Hopefully you already identify these things that Anna was talking about before, and Lorian has actually been involved in generating. So this is the experiment done in Paris, and what they saw is that if they quenched the system, then they would get actually persistent currents occurring. Okay, so phase, as you're quenching the system, grows locally. So if the local phase joins up, it's possible that it joins up to something like a +1 or a -1 or +2 or -2, but most of the time it will join up to 0, and so you will get no persistent current. And you expect the spread around 0 on the number of these persistent currents or the winding numbers. Okay, so how do we actually model this numerically? So the idea is quite a simple and generic idea. Let's just take the most general case. Let's assume I have a system and I want to ask, how does that system equilibrate to a bath, which represents its environment? Well, we know it will exchange energy and particle number. So I can write the evolution of my system in terms of whatever characteristic system evolution there is, along with two terms. One term that transfers particles in and out of the system with the bath. And because this is random and stochastic, there's associated fluctuations and a kind of fluctuation dissipation relation between those two parts. Okay, so what is our system here? Well, imagine you have all the atomic states. Our system is basically all the modes that are effectively affected by the presence of a condensate, okay? All of the modes that are highly populated, these so-called classical modes, where basically you have a population of more than one particle per mode on average. And the bath is basically all the higher-lying modes with which these lower modes are actually interacting with, okay? The characteristic Hamiltonian is nothing other than the Gross-Pitevsky Hamiltonian for this system of cold atoms. And so the idea is we basically model everything by this equation, by this Langevin equation. Okay, the actual equation we solved looks a bit different. Okay, rather than having a minus IR phi that I was showing before, in some limit by saying that you have many particles per mode, you can approximate this by a classical distribution. You're giving away Bose-Einstein distribution to Rayleigh genes, and then you can write it as 1 minus some characteristic parameter, gamma, your Hamiltonian plus the noise. And then the correlations of the noise are, of course, associated to this growth parameter, gamma here. Now, when you solve this equation numerically, in a statistical sense, one run of this equation corresponds to one numerical run if you've put all the right parameters for the system here. Okay, so you can have many different external control parameters. If I look at this equation, what are these parameters that I can do? Well, there is the growth parameter, this gamma here. There is the chemical potential of the system, which ensures what the final equilibrium will be in conjunction with the interaction strength, G. And the temperature also enters in the noise. The higher the temperature, the more noise there is, the more fluctuating the system is. Okay, so I'm going to apply these in the context of this experiment done at Trento, which was an elongated 3D experiment. Okay, so in that experiment, they claimed they saw the spontaneous creation of Kibble-Zurek solitons. It emerged later that the defect is a little bit more complicated because it's an elongated geometry. It's kind of a squashed vortex, which is called a solitonic vortex. But this is not really so important for what I'm discussing here. And they've characterized that in follow-on experiments very well. So what they did is they observed that as the system expands due to those different domains, they could see these dislocations in the expanded images, which were characteristic of different domains of phase in the system. Okay, so they started with a system at quite some high temperature. They cooled to some temperature a little bit above the critical point, and then they imposed a continuous cooling ramp to somewhere below the critical point, not quite to zero, but sufficiently below the critical point. And then they observed things. You can see here how they're observing from the different axes, and then they could actually count the number of defects. Okay, so how do we implement that in the numerics? Well, what are the things we know? We know roughly the starting point that they had, about 800 nanokelvin and about 2 times 10 to the 7 particles. And we know, although every time it was slightly different, we know roughly what the average final thing that they would get at the end of the quench was about 200 nanokelvin, about 1/3 of the number of particles still in the system. Okay, and this is not a perfect condensate. It would have something like 75% condensate fraction. So what we need to do is to feed that into the way we solve things. So we have 2 control parameters. One is the temperature. So we do a linear ramp, cooling ramp in the temperature. Okay, we can control the time scale over which we have the ramp. That will set how quickly we are scaling. We're crossing the phase transition. And simultaneously, we are changing the chemical potential and fixing it to values such that the initial atom number and final atom number will match. We don't include any atom loss or anything else. It comes through this chemical potential. Okay, so let me show you a movie now of what happens, and then I'll explain what is shown. Okay, so what you see here is a thermal cloud, an incoherent thing being cooled through the phase transition. And what you saw is this noisy initial low density thing suddenly became very fragmented with these purple lines, which are the defects that are generated spontaneously. And then the density is growing overall. So you get this formation of these green regions where the density is growing, and you have some defects that are trapped into the system. Okay, having described it, maybe let me plate once again, so you can see the early time, how it, of course, how fragmented it becomes has to do with how quickly you're quenching through the transition. You see between these vortices, you get density. These are patches of sort of fixed phase, and then gradually the phase is growing everywhere, but all these defects have been trapped into the system. And then it takes a long time to throw these defects away, because now there's a lot of volume for them to move. And so here we're seeing at this late time evidence of the nature of the system, which is, okay, so we have a thermal gas, it crosses through the critical point, okay? It has some delayed time dynamics where it becomes really fragmented, and then it starts growing gradually, okay? It's very complicated behavior. There's a lot of, these pictures look very similar to the ones that Vanderlei showed, starting from a turbulent thing and having all these vortex rings and vortex lines in, but of course from a very different starting point. And then we go into this phase ordering phase, and eventually we get, unless we wait for very long, we'll have a couple of defects possibly trapped there. It depends on the parameters, of course. Now, what we have is at this delay time, we have many modes. Here, remember what I'm showing you. I'm showing you this largest eigenvalue. At this point, there are many, many eigenvalues that are equally relevant. So if I look at any one of them, it will look very fragmented. It's only the sum of them that will give me the density. Okay, so here I have really a quasi-condensate, or what I might loosely call a turbulent or a chaotic state. Okay, the Penrose-Sager mode starts dominating gradually. You see here now, at this point already over here, I have one mode which is a few times more populated than all the others. Okay, so I can start thinking about a Penrose-Sager mode, and then comes the phase ordering stage until I get to what is my final state. Now the point is, Kibble-Zurek, I don't know why it does that. Kibble-Zurek physics only applies here, okay? While you are crossing the phase transition. Everything else is a relic of crossing the phase transition as visualized in whatever you can image. And most experiments that have studied vortices in Kibble-Zurek have actually looked at them after a very long evolution time and after possibly a long expansion time as well, okay? So it's not really directly, it's probing indirectly Kibble-Zurek, but it's not seeing directly what is happening at the point. Okay, so if I look at three different regimes, if you like, if I go very slow, I basically almost grow into a condensate. If I go immensely fast, I have a lot of defects trapped in, and there's still defects at the very end. But in general, I want to focus on this typical intermediate regime where this Kibble-Zurek scaling will apply. So how do I want to characterize things then? Okay, so we're starting with a system which is equilibrium, and it's being driven. Initially, it's following these equilibrium states. Okay, so I can think of it as equilibrium. At some point, it will break the symmetry. So the dynamical system looks very different from the corresponding equilibrium system. And then eventually, at the very end, it will re-equilibrate. And so the dynamical and the equilibrium system will look the same, okay, for the same parameters. So I can characterize that by looking at the difference in the scaled correlation length of the system between the dynamical driven one and the corresponding equilibrium one for the same chemical potential and temperature at any time. And what I expect to find is, well, the equilibrium one, this axis now is time, but for the equilibrium one, you can think of it as different values of temperature and chemical potential. So the equilibrium one at the critical region will diverge. Eventually, it will saturate the finite size system, and you have a lot of coherence. If you look at the dynamical one, it only starts reacting after this certain delay time, and it grows a lot more slowly and a lot more messily because there's a lot of defects in here that the system has to shed away to equilibrate. So I can do a cartoon where all of the runs will actually satisfy this kind of picture, but this is kind of a qualitative rather than a quantitative picture. If I look at this difference in parameter initially, equilibrium and dynamical correlation functions. What was that? Equilibrium and dynamical correlation functions are the same, but then the system falls out of equilibrium. The dynamical system has not reacted, but the equilibrium system has reached a lot of coherence. So there's a big difference between equilibrium and dynamics. Then it takes some time for the dynamical system to start catching up. And when it does, depending on how quickly you're quenching the system and so on, it will eventually relax so that the dynamical correlation function matches the equilibrium one for the set parameters. And to be able to do that, we need to self-consistently determine where is the critical point in our simulations. So we do that by doing the whole sort of condensate fraction diagram as a function of temperature and comparing against experiments to make sure we are modeling what we would like to be modeling. So this is basically the kind of picture now you see from very noisy to very well coherent. And then as the system breaks asymmetry, this is the cartoon that I showed you at the beginning. The system crosses to the critical point. There's some delay time before the dynamical system starts evolving. And then there is this phase ordering process. Okay. I mentioned about universality and the idea that we can scale things out. So far, I've just shown you qualitatively what is happening. So let's try and quantify this a little bit. So what we want to do is study different quench ramp durations, so different parameters tau q, and we want to parameterize some things. So we'll be looking at the coherence length of this Pedro-Zonsager or condensate mode, and we'll also be looking at the zero momentum mode occupation as an indication of the level. I mean, that's not really a definition of a condensate, but it's still characteristic to look at that. So if I have, I look at that as a function of the distance from the critical point, okay? And I vary the ramps from a very slow ramp to a very rapid ramp, and I see a very different behavior. And if the ramp is very rapid, like the red ramp here, then sometimes I get some defects trapped in. So when I try to measure the correlation length, because I have a finite number of samples and it's numerically very intensive, if a vortex is sitting somewhere in the middle, it can actually mess this picture. So this is a vortex propagating through because I didn't have enough averaging. So what we look at is what happens in this region near the critical point, okay, TC, so within this T hat. And what we do now is we scale, we can analytically figure out for our equations what are the scaling parameters. We know how to scale out with T hat, and we know what is the characteristic psi hat, okay? And so we can scale things out. And what you can see is all the way up to about 1 or maybe even 1.5 T hat, everything falls onto one curve very nicely, okay? So this is this evidence that we can actually apply this universality in the region of the critical region, okay? And we can see how very different dynamics looks very similar in that point, and we can characterize that very well. We have a lot more information in the paper on that. So now we've crossed the phase transition, we have created a very non-equilibrium state. And the question is, how does that relax? And what's going to happen is all these vortices or all these defects will have to untangle, and we have to get this largely coherent system that forms at the end. Okay, so let me tell you some of the gist of the findings that we have. So if you look at it, of course, what's happening is the number of defects is decreasing. Okay, the density is growing and the number of defects is decreasing, signaling an overall increase in the phase coherence. Now, what happens to the nature of defects? This is a rather messy system. It's an elongated 3D gas. Okay, so what happens is early on, the system is growing effectively homogeneously. There's a core at the center, which you can think of it as a circle that then grows out to fill in the ellipse of available space due to the trapping. So the random initial defects actually become these so-called solitonic vortices. You can think of it as something that has a 2 pi phase winding, but the phase winding is concentrated. It's non-linear as you loop around, okay? So these are these defects, and these are very long-lived in the trap, and these are the ones that have been observed and since studied a lot, actually, in this experiment and elsewhere. So gradually, as it's cooling down, basically it adapts the properties of the system it's in. So you start seeing the role of the inhomogeneity. Now, if you look at the defect number as a function of evolution time after the transition, you see that in the very rapid quenches, you have a large number of defects generated, and it decays initially very quickly and then more slowly. If you go very slowly, you don't generate that many, and they decay as well quite quickly. But what happens if you look at late evolution times, there's not that much difference like there is at early evolution times, right? So the system reaches a plateau. So the Kibble-Zurek scaling says that the defect number will scale linearly in that way with the quench rate. The exact rate of the exact exponent depends on the system, depends on the geometry, dimensionality, and so on. But the when you go to very fast quenches, okay, then what happens is you get a lot more defects. And when you get at the late time, it doesn't really matter. You have more defects, but it's a plateau. So you see this deviation from Kibble-Zurek behavior to a saturation for different quench rates. And this has been seen in many different experiments. I'm just focusing on one. So if I now look at my late time images, these are the images I showed you from the experiment, and I tried to reconstruct, well, I'm running the code, and I chose the ones that look a bit reminiscent of that. You see, we have at late times things that have 1 defect, 2 defects, 3 defects, and so on. And we can look at them in situ. We can probe G1, G2, and so on. Okay, so people are interested a lot in the context of sort of turbulent relaxation dynamics. And so we thought of asking the question as well, what does the vortex line length actually do in the system? As the system falls out of equilibrium, I have a lot of vorticity. How does that relax? It's a very hard thing to probe, so we haven't included that in the paper, and it's not a very detailed characterization. It's more to show you an idea of how things are. We see the vortex line length, and after it's generated, when the system falls out of equilibrium, it decays, and how quickly it decays has to do with how noisy the system is, how we are quenching the system. But we were trying to characterize, there's a sort of characteristic decay exponents, if you like, for unsustained quantum turbulence. And the exponents have different meaning. Vanderlei talked a bit about that. So t to the -1, t to the -3/2, whether you have this ultra quantum turbulence or whether you have this Kolmogorov turbulence, we couldn't really tell. I mean, we don't have enough resolution of runs. In principle, we might be able to. It might not even be the right question to ask, but it was just interesting to see how that goes in the context of starting with a well-formed condensate and exciting to turbulence, as opposed to coming from above the critical point. Okay, so if we want to understand things better, then we should be looking at something a little bit cleaner in 2D to see this idea of phase ordering. And so we looked at phase ordering in a 2D homogeneous gas, where you expect to have very clearly identified self-similar dynamics late on in the phase ordering. So in 2D, as you know, you don't have Bose-Einstein condensation. So what we have is this different algebraic order decay of the correlation function. And we use this to characterize, I'm not going to go into detail, but to identify exactly where the critical temperature is for a system so that we have a way to normalize against our dynamical simulations. And then we wanted to understand how does, in a realistic system, the dimensionality change as we are changing the parameter. So this is for the context of the Paris box experiment, but these are now sort of generic types of experiments where you have a planar box, and then in the other direction, you have a harmonic trap, and you're changing the degree of confinement in the third direction to actually see how 3D or 2D the system is. Okay? So what we wanted to see is, well, what are the characteristic things? Firstly, we wanted to identify that we're correctly seeing the 3D and the 2D limit in these systems. And so we did this by looking at the fraction of particles in the dominant eigenmode, so in the condensate, in the case of 3D, by looking at the relative importance of the eigenvalues. If one eigenvalue is very dominated, then you have a condensate. Okay, that's a very clear signature of condensation. And there's another thing that people use in phase transitions called the Binde tubulant. It's associated basically to, if you like, to this local density fluctuation or local quasi-condensation or so on. And so this thing jumps from across the phase transition. So we can use all of these to identify where the phase transition is. And we did that very systematically. I'm not going to go through the details about changing the confinement in the third direction, just to see what is 3D and what is 2D. Now that we've identified the limits, and each of these bands is showing our uncertainty in determining the critical temperature as we are changing the confinement basically vertically. And so with that, we were able to identify the dependence of the critical temperature on this dimensionality parameter lambda, which tells us the confinement in the third direction. Okay, so we have the 2D limit. We reach the 3D limit. We're not exactly 3D. In principle, you would have to go to much higher, but we are more 3D than these box experiments that are done and doing 3D physics. And also we see this shift in TC as you would expect from this is the non-interacting one shown there. So this is the how much the system is changing. Okay, and of course what we want to study, but we have not studied yet, is quenches as a function of dimensionality crossover. But that we haven't done. This is just a schematic from simulations to show you the kind of physics that emerges. So we now, having identified this thing, we can go to the 2D limit, okay, where we just have effectively point vortices. And what happens is after the quench, or if you like, long time after an instantaneous quench, basically you start getting all these random domains and you get few domains surviving, okay? And there's a characteristic length scale of these domains in the plane. And we know that if this length scale becomes much larger than all the microscopic system length scales, basically we have universal features. So it's independent of microscopic details. So we will get self-similar evolution in terms of R over this characteristic length scale in this scaling regime. Okay, so we expect to have a correlation, first order correlation function that looks like that, everything collapsing onto it. And indeed, this is what we find as vortices, vortex-anti-vortex pairs are being destroyed here. We can look at this, the form of this universal correlation function as a function of R over LC. We can characterize how this characteristic length LC grows, or how the number of vortices actually decays. And we can relate that to the dynamical critical exponent of crossing the phase transition, and everything matches very nicely. And one of the questions is, well, what is the role of open versus closed system? Okay, and are cold atoms, for example, really open or closed? What we have looked at is simulating with just Gross-Pitevsky, or also having a system where we have this stochastic Gross-Pitevsky, so we have a coupling to the bath. And when it's dissipative, you expect to have this kind of behavior in 2D. So you expect to have logarithmic corrections, and you expect to find exactly the dynamical critical exponent Z to be equal to 2. But we find that in the context of Gross-Pitevsky equation, actually, of course, you don't have the logarithmic corrections, but you also get something that, something that is a slight deviation from 2. It would be very hard probably to characterize that in experiments, but this is actually very, very carefully done. And so we're very certain of that. We see a crossover between the two. I should note that a lot of these things that I have talked about, we have actually done with Marcena Szymanska in the context of driven dissipative, so extern polariton condensates, and also Jacopo Carusotto. And we have seen the same generic thing. So we have identified Kibble-Zurek scaling in driven dissipative extern polariton condensates. We have found these exponents to be exactly Z equals 2, this dynamical critical exponent with the logarithmic corrections and so on. So it's all as would be expected. So with that, I've come at the right time to a summary, but I have two more things to say after the summary. But let me just summarize. So I hope I've given you this idea that quench quantum gases are actually quite interesting systems to study. This both universality, but also non-equilibrium physics. I hope I gave you a complete picture of how something from equilibrium falls out maximally out of equilibrium and then gradually relaxes through this phase ordering, and what is the role of the potential and the trap. We characterize this in the context of this cartoon Kibble-Zurek mechanism, and I showed you how there's this, in that regime, a characteristic time scale and length scale for everything. Everything is consistent with experimental findings and with what you would expect, but we also see something which is not possible to be seen directly in the experiments, how the geometry as the system is growing basically affects the late time dynamics in comparison to the early time dynamics, because we have a probe of all of that. And this raises these open questions. What's the role of trap density and homogeneity and so on? Very interesting questions. So a couple more slides. As I said, firstly, I'd like to promote, some of you will know this journal. I know a couple of you have published in here, Communications Physics. Okay, it's the latest in the Nature journal. So it's not Nature Communications, as sometimes referees seem to think when they're sending me reports back. It's It's lower than Nature Communications, but it's only for physics. So I would really like to encourage papers. I'm trying to build up the cold atom or condensate community, and it's starting to increase a lot. But I think it's a good time to publish there. Of course, it has to be a valuable paper that I'm sure you will know if you submit there, but I would really like to encourage more papers in this field. That's one thing. The other thing, I should acknowledge people. So the one I would primarily like to acknowledge is Gary Icahn Yu. And if you're looking for a numerical guy, he's the perfect guy. Okay, he's the exton polariton things were done on my part from Paolo Comaron, who's now working with Marcena. Sorry, I get excited. My fingers are too big. And so there's a lot of other people. There was a collaboration with experimentalists at Trento and also with Jacek Giamaga for this Kibble-Zurek stuff. And it's a very interesting and rich field. One thing I'd like to leave you is just with one concept. I don't have time to discuss that. But actually, it was mentioned very briefly by someone early in the conference about this dark matter being a condensate, this very cryptic message, okay? There is an increasing community of cosmologists and very, very credible cosmologists who do proper dark matter simulations, who have this idea that basically dark matter could be an ultralight axion, mass 10 to the minus 22 eV, really, really light, not the QCD axion or anything. And if you put the numbers in, then this has de Broglie wavelength, which is basically the size of a galaxy. And so then there's this idea that you can actually solve dark matter by looking at basically Schrodinger, or even with interactions, a Gross-Mitaevsky equation coupled to a Poisson equation for gravity. And we've done some simulations of that. And what I would like to leave you with, and I have a lot more to show anyone who's interested, is basically, this is a picture of fuzzy dark matter. This is an isolated galaxy at the center. It is perfect, 100% condensate. We have done the Penrose-Onsager mode, all the analysis. It's not about quenches, it's about seeing the static properties here. Around it, the coherence drops very rapidly over a length scale. And beyond that, it matches the experimental observations of this so-called Navarro-Frank-White NFW profile at large distances from the core of a profile. What is really interesting is all around it, it is actually a quasi-condensate. There is long sustained vortices, there's regions of overdensity and underdensity, and they don't have the same phase, at least in this context, and they're interacting. So there's basically a condensate in the middle with a non-condensate all around it. And so if you like, this is the standard picture we have in cold atoms, and this is the corresponding picture in fuzzy dark matter. And with that, I've used up all of my time. Thank you very much for your attention.
Thank you, Nick, for this very interesting talk. Questions?
So, Nick, how is this related to modulational instability? Because this is a mechanism that when you quench from positive interaction to negative interaction, you generate a soliton train.
Right.
And it has characteristic length scales and time scales that look kind of similar to this. Have you looked into that?
Yeah, no, I haven't looked at it in the context. So modulation stabilities are, of course, there and have been studied a lot. I'm not sure that, I mean, you could necessarily cast Kibble-Zurek in this context of modulation stability, but
what would that hinge on? What would you?
Sorry?
What would that hinge on? I mean, in what respect would it be the same or not the same? How would you differentiate between them?
I don't know how you would differentiate, because it is an issue, obviously, of reaching some kind of characteristic, like momentum or something where things would go unstable, right? Yeah. And it's true here, you have a characteristic length scale, so there will be a characteristic momentum, but I cannot say anything more coherent. This is the good question, but I cannot answer.
Because that's a really big field.
Sure.
There's a lot of people who have done modulational instability in the context of solitons.
Yes. Yeah. So thank you. I haven't thought about it in that context, but you're right.
So you mentioned this Esslinger measurements from 2007 or so. The surprising thing is that although they had a harmonic trap, they found the homogeneous critical exponent nu.
Yes.
And according to my knowledge, has been no RG theory whatsoever to answer the question whether the trap is now relevant or irrelevant for the critical exponent. My question to you is, did you determine nu from your simulations? What is your experience?
Sure. So we tried very hard to answer that question. The numerics is immensely costly, and a tiny bit of shift changes this nu so much, which is why I'm very impressed and somewhat perplexed about how accurately it was measured in that experiment. And I've also discussed that with Tillman. There were some assumptions that went into getting this out, very sensible ones, but there were some assumptions in getting. What we found was, I would say, of the order of about 1/2 to 0.7, but we didn't have anything concrete enough to be able to characterize. We did try, and we were very interested in exactly that problem. But I have to tell you that in a 3D inhomogeneous system, it is, I mean, it's already very hard. We tried with Paolo and Machen and other people to characterize this, for example, even in 2D, and it's already hard in 2D numerically. In 3D inhomogeneous, it's very, very hard. So I don't have the answer to that question. So it remains, as far as I can say, an open question. It's a very valid point. Thank you.
And the subsequent question, you mentioned this dynamical critical region.
Yes.
But there's also a static critical region defined by the Ginzburg criterion. So if you are outside of the Ginzburg criterion, you have mean field exponents. Inside, you have non-trivial exponents. So my question is, does this magnitude of the Ginzburg interval play any role for analyzing the Kibble-Zurek?
So in principle, when we are looking, for example, here, we're always looking in the region where it has grown. So possibly we are sort of automatically restricting our analysis in that sample. So what we have not looked at is what would happen outside that, to try and see what is the difference to answer that question. So it does absolutely. So what we can see in our simulation, we can see that there is a growth. What we even looked at is to try and characterize whether this is a homogeneous Kibble-Zurek or an inhomogeneous Kibble-Zurek. And the best answer I can give you is basically, if you do some toy modeling here, this looks like these experiments are actually completely within the homogeneous, even though it's a trap Kibble-Zurek mechanism. But actually, if you look at the exponents, if you look at the slope of the Kibble-Zurek, because these defects grow into the geometry, it effectively, you have to account for the trap in order to get the correct exponents. So, but at very early times, it's basically homogeneous Kibble-Zurek at play. And one big question is, can you create an experiment that controllably will allow you, it's something we're looking at, to see that you're getting inhomogeneous effects at play, and what are the relevant length scales and so on. Thank you.
Hi, Nick.
Hi.
Well, I have two simple questions. Normally in physical system that we see domains that have to form a whole. Normally small domains will be sacrificed and for the big domains to grow. And I could not see very well in your simulation, but that not seems to be the case. The things only grow. Why? Why small domains that form and say, well, it's easy for me to dissolve back.
Okay,
and
so think of having like a system here, and it's smaller domains because they're separated by defects. If you look locally, you will see the number of defects going down, and so you're getting the smaller domains disappear first, actually, and grow.
Yeah, we see that in the
if you look carefully. So I mean, we can look at movies and images. We have
so
like
then there is a critical
images.
size for the survival of the domains.
Well, we haven't characterized, and it's very hard, but we do see very small domains that then will actually expand. But obviously the vortices are also, we see the vortices moving about. And the way we probe vortices is actually by looking at the high velocity field. So we're not directly probing all the vorticity features. We're looking at high velocity field. So we don't have, like you did, for example, in the analysis of your experiment, the full classification of what is a loop and what is a line. And it's very hard to address those questions, but we do see loops growing. But what happens and why you don't see that clearly in the movie is what's happening is the system is growing rather rapidly.
No, the system is growing,
that's
but
taking over sort of in your sort of visual interpretation. We do see these small domains actually growing, absolutely.
no, I see, but you see big domains, and then there is small domains, and the small domains have to disappear for the big domains to grow.
Generally, what's happening is, so what we're looking at here is just one of these modes. Remember,
All the domains cannot grow at the same time.
No, but we have many different domains, right? So
Yeah.
what's happening? We're looking at the single domain of the system, and the whole gas is the sum of them. So what's happening is it's growing in that particular domain. You know, so.
Well, the second thing is, some time ago, we considered the inverse Gibbs rate.
Yes.
And you think it's possible? Instead of starting with the thermal and see, well, how the condensate is formed, I start with the condensate. And then I say, well, the system will go the opposite now.
I think so. You will not have exactly the same scaling, but I'm pretty sure you will see some universal features. And this is the kind of question
that's the question. Would we see universal features?
I think you would see universal features if you would do that. I don't know what the role of the trap and everything would be, because now you're starting with something which has a set geometry, which could be rather restrictive.
What? No, we start with a big structure. No, Randy.
Yeah, but you excite. You start with the condensate. Excite.
We're going from the condensate to the thermal cloud at the end of the day. He goes from the thermal cloud to the condensate. No, I know, but what I'm doing, you see, what I'm saying, the inverse is exactly this. We start with a very, very big order, the condensate, but then you perturb, you take the system artificially to some position that defects appear, and that goes to turbulence, and that decays to a thermal cloud. This is the opposite of this type of phase. Well, we can.
And I think we can discuss, but I think the generic question that I've already posed to you.
I was wondering now if what we see of
Yeah.
scalability and everything may be related.
What would be interesting is starting with thermal cloud and quenching in a certain way this non-equilibrium state right after crossing the transition, and starting with some kind of condensate and exciting it, but in a very, very violent way. And what I think would be interesting would be to study the actual properties, how different these non-equilibrium states are, and the relaxation after them. And this will connect to this issue, whether they are these non-thermal fixed points, are they different? And
now I'm moving that way. I'm moving the system towards the initial, the thermal cloud.
yes, yes. But what I'm saying is, what is interesting is you start here, you start there, you're moving in this direction, you get here, you have something super non-equilibrium. Analyze that. I mean, if it's a true non-equilibrium chaotic state, it won't matter which way you came from.
Okay. Any further questions? If not, I'll just ask. I'll make a comment on this final part on dark matter. You need something like 10 minus 22 electron volts for the candidate, and the problem is that you don't really have any particle physics candidate for this. So if it was the axion, the mass range is 10 to minus 5 electron volt, wherever something. So you don't really have this. You cannot solve with a particle, a direct immediate extension of the standard model, the problem of dark matter, right? So you
but there is this idea, as you know, in particle physics, people sometimes invent particles and try to study the thing. So initially, such things were studied, and people like Sikivia, for example, studied that a lot. The idea of taking the QCD action 10 to the minus 6 EV and trying to see, and they also had the concept of thermalization. And then there was a paper written that basically the ideas are right, but actually for the QCD action, the context of thermalization would not be correct because the timescales did not match. And that is what seeded this idea. But the concept of cosmological condensation with different masses has been around in different communities in different ways, but it's the same idea. I mean, there's the issue of what causes thermalization, what causes this randomization of things, but it does cure some problems of cold dark matter. So the thing to show is this, which is not my simulations, which seeded this field. On the one side, you see cold dark matter simulations. On the other side, you see fuzzy dark matter simulations for many galaxies. It's exactly the same structure, but on top of that, the fuzzy dark matter cures all the problems near the core of galaxies, which is a big problem for CDM, but could be cured by adding baryonic matter, the coupling or a different field. And there's all kinds of, it's a zoo of models of what people are proposing to fix the problem. So this is just another one to this one.
Well, probably the quantum fluctuations also could solve the problem in the spirit of the droplet, but then we can discuss this further.
Yes.
So I think we are now ready. We can thank the speaker again.
Thank you.
And I will give the word to the organizers.
I'll go to the poster section. We have a coffee break, and then we have a poster section.